Hello and welcome to Lecture 8 for Unit 3 of Intro to Logic. We're still doing derivations and predicate logic, and today I'm going to talk about strategies and steps. That is, what to do if you don't know what else to do when you come across one of these derivations. So, in Unit 2, I gave you a chart of what kind of derivation to do for what kind of show line. And this is the same chart, I'm just adding to it. The only thing I need to add to it is one line for existential statements and one line for universal statements. Everything else is the same. Now, unfortunately, my tablet here doesn't show the fancy script letters as fancy script letters. It shows them as big A's and B's. But those big A's and B's are placeholders for any statement of a certain form. So when you're trying to figure out what kind of derivation to do, look at the show line. And if the show line is a certain form, my recommendation is on this chart. So if you're trying to show an atomic statement, that's something like FA or RAB. The advice is to do it by indirect derivation. You assume the negation of the atomic statement, like not FA. You have a new show line to show splat. If you're trying to show a negation, it doesn't matter what it's a negation of. It could be a negation of an if-then, it could be a negation of an or statement, negation of an and statement, negation of an if-then statement, even a negation of a quantified statement, like an existential statement or a universal statement. The advice is to do it by indirect derivation. You assume the thing without the negation on it, and then you try to show splat. Also do an indirect derivation if you're trying to show an or statement. So trying to show A or B, indirect derivation, assume the negation of the entire or statement in parentheses. Use show line to show splat. I'm also going to give you the advice if you're trying to show an existential statement, that if the main operator of what you're trying to show is a backwards E, that would also be done by indirect derivation. You assume the negation of the existential statement and try to show splat. Now, most existential statements can actually be shown by direct derivation, but there are a few that can't. So I'm going to give you the advice of doing it by indirect derivation. If you can do it by indirect, you can also do it by, if you can do it by direct, you can also do it by indirect. So it's never going to prevent you from finishing the problem if you do it by indirect. Next, if you're trying to show an arrow statement, A, arrow B, do it by conditional derivation, assume A, show B. If you're trying to show a universal statement, that is an upside down A statement, for all x something about x, you do that by universal derivation. For universal derivation, there's no assumption. You just have a new show line to show an instance of the universal statement with a new name. So we talked about universal derivation a few lectures ago. Finally, if you're trying to show splat, you just do it by direct derivation. If you're trying to show a biconditional, it's a two-way arrow statement, you break the problem into two subproblems. You write direct derivation by that one, but then first you show A arrow B, then you show B arrow A. At the end, you put them together with double arrow in. If you're trying to show an and statement, you usually do that by two indirect derivations. First you show A by assuming not A and getting a contradiction, then you show B by assuming not B and getting a contradiction. Then you put the two together at the end by ampersand in. So for those two kinds of statements, you break the problem into two subproblems. So we'll look at an example of that in a bit. Now, not only am I going to give you this chart for advice of what kind of derivation to do for what kind of problem, I'm actually going to give you a whole algorithm that is a whole series of steps for doing any kind of statement. Now, I'm not going to suggest that you try to memorize these steps, but I do want you to get a feel for them. If you do enough examples where you have these steps in mind, you'll get a feeling for them without memorizing them. But this is basically what the computer does when I ask the computer to do a derivation. So you know if you do the homework exercise, the textbook exercises, there's a button, give full derivation. I didn't give the computer the answers. What I did is I taught the computer how to do these problems, and this is the method it uses. It doesn't always give you the most efficient proof, most efficient, shortest derivation, but it always comes up with something. So this is something to fall back on if you don't know what else to do. So there are basically 7 steps. You start by looking at the show line, then you look at the chart and you figure out what kind of derivation to do, and you set up the right kind of derivation. Then step 2, you look at the new show line. If the new show line is show splat, then you can proceed to step 3. If it's not show splat, you go back to step 1, you look at the chart and figure out what kind of derivation to do, and then you set up the derivation for that kind of derivation, and you repeat steps 1 and 2 until you get show splat. Once you get show splat, that's when you start applying the other rules to try to get your contradiction. Step 3 is to do the negation rules for the quantifiers, not existential out, not universal out. So if you have any negated quantifiers as main operators, you can do those negation rules. Then you want to do existential outs, and you use new letters when you do existential outs. Then you want to do universal outs. So the most important thing about this series of steps is that you do step 4 before step 5. You do existential outs before universal outs. Step 5, do universal out for every universal statement. Now, sometimes it makes sense to do universal out more than once. So you'll do universal out for every letter you have in the problem. If you can't figure out which ones to do, just do universal out to every letter you have in the problem for every universal statement you have. Then you apply the other rules, that is, the rules like existential in, the rules we learned in Unit 2, to try to get that contradiction. Finally, you look to see if you've gotten a contradiction. If you have, you can write in splat and cite splat in. If you haven't, then you may need to go back to step 3, repeat steps 3 through 6 for all the other new statements you've gotten, and you keep doing that until you get a contradiction. So let's see how this procedure plays out with a few actual problems. So let's look at this one. Step 1, there is an x for which if hx then fx. Step 2, for all x, if not hx then gx, show there is an x, fx, or gx. So we start by looking at the show line. The show line tells us what kind of derivation to do. So as I said, oftentimes you can do existential statements by direct derivation, but occasionally that's not true. This is actually one of the cases where it's easier to do it by indirect derivation. That's what the chart says. If you're trying to show an existential, do it by indirect derivation. So we're going to assume the negation of the entire existential statement. That's our assumption. And a new show line to show splat. So that's step 1. Step 2 is to look at the new show line. If it's show splat, write direct derivation and proceed to the next stage, step 3. Right, so we can proceed to step 3. Step 3 is to do any of the negation rules for the quantifiers. So not existential out, not universal out. For step 3, we can do not existential out to line 4. We get a universal negative. It's not true that something is, then everything isn't. So the negation moves to the other side of the quantifier. In 4, the backwards e changes to an upside down a. So that's 4, not existential out. There aren't any other negations before quantifiers in this, so there's nothing else to do for step 3. Step 4 is to do existential outs. So we have an existential out to do on line 1. Right, there's a backwards e as the main operator. So we'll take off the quantifier in line 1, change that x to an a. We have to use a new name, but there are no a's anywhere, so we can use a for this. So that's 1 existential out. That's step 4. So step 5 is to do any universal outs to every every letter we have in the problem. So we have 2 universal statements. We have one at line 2, we have one at line 6. We're going to do both universal outs to all the lowercase letters we have in the problem. There's only one lowercase letter, that's a. So I'll do line 2 to a, and I get not ha, arrow ga. And I'll also do line 6 to a, and I get not, in parentheses, fa or ga. So that's step 5. That's very important that we did step 5 after step 4. If we had done step 5 first, if we had gotten lines 8 and 9 before line 7, we wouldn't be able to use a, because a wouldn't be new, and then we'd be stuck in the problem. But now, since we did the existential outs first, the universal out's allowed to use the same letter because there isn't the same restriction on universal out. Now we're going to apply the other rule. So I'm going to start by line 9. I get not fa by not wedge out, right? Both sides are false if an OR statement is false. That gives me what I need now. I can do modus tollens on line 7. I got not HA, right? If HA, then FA, but not FA. So I have 7 and 10, arrow out. That gives me what I need to do modus ponens on line 8. So I get GA. If not HA, then GA. If not HA, so that's 8 and 12, arrow out. So that's step 6. We're doing the other rules to try to get a contradiction. So now with step 7, we look to see if we have a contradiction. we have a contradiction between 11 and 13, we write splat, 11, 13, splat in. So now I've shown splat, and I've shown this by indirect derivation, and I'm done with the problem. Nope. That was supposed to be 4 existential, 4 universal out. Sometimes I make those kinds of mistakes. Sorry about that. No, 6. Sorry about that. It's early morning when I'm recording this, and I'm a little bit out of it. 6 universal out. Sorry about that. All right, let's do this next one. So you want to look at the main operator of the show line. That's the first step. Look at the main operator of the show line. They'll tell you what kind of derivation to do. This is an OR statement. It doesn't matter what's in the OR statement. If you're trying to show an OR statement, do it by indirect derivation. Have the negation of the OR statement. All right, so we have negation of an OR statement. So we got a new show line. So step 2 is look at the new show line. The show line is show splat, write direct derivation to proceed to step 3. So step 3 is to do any negations of quantified statements that we have. Now, the negation in line 3 is not applied to the quantifier, so we can't do not existential out on 3. So we're going to skip step 3. Step 4 is do any existential outs we have. So we have an existential out we can do in line 1. So we're going to take off the backwards EX, change that X to a new name, so I'll change it to B. Step 5 is to do any universal outs that we have. So there are no universal outs to do. There are no universal statements. So I'm going to skip step 5. Step 6 is to apply the other rule. So I'll apply not wedge out to line 3, and I get not backwards EX RXA, 3 not wedge out, and I get not backwards EX RAX, also from 3 not wedge out. Well, there aren't any other direct derivation rules to apply, the normal direct derivation rules to apply, so that's the end of step 6. Step 7 is to look to see if I have a contradiction. I don't have a contradiction yet, so I have to go back to step 3 and repeat steps 3 through 7 until I get that contradiction. So go back to step 3. Step 3 is to do any negations of quantifiers. Now I have negations of quantifiers, so when I repeat, I can change the backwards Z in 6 and 7 to the universal negation. So if it's not true that something is, then everything isn't. So 6, not existential out, gives me that. I also get for all X, not R AX, from 7, not existential out. So when I repeat, I'm getting down to step 4 now. Step 4 is doing existential outs. Now, I've only done existential out on line 1. There's no other existential statement. So you don't do existential out in 6 and 7 because existential is not the main operator. So I'm back to step 5 now. So step 5 is do universal outs. So I do universal out on 8 and 9. If I do it to every letter I have, I'd get not RAA from 8 universal out. It turns out I'm not going to need that, but I can go ahead and do it anyway. Not RBA, so I'm doing 8 to both A and B. I can also do 9 to both A and B. And I'm going to get not RAA again, but I'm just doing this sort of blindly. So I do 9 to both A and B. So I've done all the universal outs I can do. Now I'm back to step 6. So now I have not RBA and I have RBA or RAB up at line 5. So I get RAB. Right, that's 11 and 5. Wedge out. Now I have my contradiction. So step 7, look for a contradiction. I have a contradiction now here between 13 and 14. I've shown that and I've shown that. Very good. So I just want to remind you how you show a two-way arrow statement. This is one of the ones where you've got to break the problem into two subproblems. So problems with a two-way arrow tend to be pretty long. Now I'm not going to follow the steps exactly in this one because I don't want to make it even longer than it has to be. But just show you how you show a two-way arrow statement, just to remind you, is sometimes you've got to break the problem into two subproblems. Now I'm not going to do that for line 3. Line 3, look at the show line, that's a universal statement. So we'll do it by universal derivation. We have a new show line to show FA double arrow GA. We show for universal derivation, you just have a new show line where you show an arbitrary instance of the original show line. Now this I can show wherever I want, but this is a two-way arrow statement. So this is where you write direct derivation. What you really want to do is you want to show FA arrow GA, then we're done with showing FA arrow GA, we'll go back and show GA arrow FA. Now this is a conditional, so I'll do it by conditional derivation. Assume FA, new show line to show GA. Now if you were following the chart to show GA, since it's a simple statement, you would do it by indirect derivation. It's totally fine to do this by indirect derivation. But I'm looking at line 1, and I can see from line 1, I'll get if FA, then everything is G. So I can get GA by direct derivation. So don't follow the chart. If you can see how to do something a different way, just go ahead and do it, right? So I get FA arrow for all y, GY from line 1, universal out, right? Take off the universal, just change the x's, don't change the y's. I have FA at line 6, so I get for all y, GY, 6 and 8 arrow out. From that I get GA, 9 universal out. So I've shown GA, I've shown this. Now, to show the two-way arrow statement, that's direct derivation. I need that exact statement inside the box. Getting the one-way arrow statement is not enough. I've got to put in a show line to show it in the other direction. Show GA arrow FA. And I'll show that by conditional derivation as well. Assume GA, new show line to show FA. And again, I'll do this by direct derivation because I can see how to do it from line 2. If you couldn't, it's totally fine to do this by indirect derivation. So line 2 will change to a universal negation. For all x, it's not true that gx and not fx. So that's 2 not existential out. Take the for all x off, change it to an A, not GA and not FA. 14 universal out. So I have a negation of an and statement changes to a, if the first one's true, then the second one's false. Now that not moves over, there's already not there, you get a double negation. So 15 not ampersand out. I have GA, so I get not FA. 12 and 16, arrow out. So I get FA by double negating 17. Undouble negating, I should say. So that's what I was trying to show. Don't need that. So I've shown that. I've shown that. Now that I have the two show lines of the two directions of the if-then, I get the two-way arrow statement. I get FA double arrow GA. And what I want to say is the two crossed off show lines. So that's 5 and 11 double arrow in. And now I've shown this and therefore shown that. Great. So we're trying to show a two-way arrow statement, do two conditional derivations, one in each direction. There's another two-way arrow statement here to show. I'm not going to do that one now because we've practiced that enough for today. But try that one on your own, see if you can do it. It's a pretty long derivation, but you should be able to do it if you break it down into two subproblems. Okay? Now, if you get stuck in a problem, there is this thing, desperate measures. Now, this is completely review from what we learned in Unit 2. There's nothing new to know about desperate measures. But if you set things up according to the chart and you follow those steps I was talking about before, if you apply the out rule to every line you have, you will get a contradiction. You can prove that in metalogic. It's something we can prove about a logical system. That if you apply the out rule to every line you have for any valid argument, you will get a contradiction. Since you only went to step 3 because you were doing show splat, that's what you're trying to get. So you should be able to finish the problem. The only times you get stuck is when you have an arrow statement or an or statement, because those two rules, arrow out and wedge out, you need something else in order to do them. Sometimes you don't have that other thing you need. If you're writing a show line to get the other thing you need, that's called desperate measures. If you're writing a new show line, if you show it, then you can use it and you get yourself unstuck. So that's completely review from Unit 2, but let's see how that actually works in a couple of problems. So let's do this problem. There is an x, rxx, or something is f. Something respects itself or something is friendly. Show that if nothing is friendly for all x, not fx, then there is something that respects something. There is an x, there is a y, rxy. So we're going to set the problem up just like it were any other problem. We're going to start by doing a conditional derivation, since this is a conditional. We'll start by assuming that nothing is f. Everything isn't f. New show line to show that there is an x, there is a y, rxy. How do we want to show this? Now, if we're following the chart, we would do this by indirect derivation. So that's how I'll do it. That's not necessarily the shortest way of doing this problem, but that's the way I'm going to do it. So when you do an indirect derivation, you assume the opposite of what you're trying to prove. So we'll assume the negation of the existential statement, and we'll try to show a contradiction. Okay, so that's basically steps 1 and 2 of the procedure. Step 3 is to do any negation rules we have. So we can do a negation rule on line 5. We get for all x not, there is a y, rxy. We just put some negation through the first quantifier. So that's 5, non-existential out. Step 4, we're doing existential outs we can do. Now we can't do existential out on line 1. The existentials are not the main operator. So we want to use line 1, we got to do wedge out. All right. So there are no existential outs to do. Universal outs. Now we could do universal out on step 3 or step 7, but there are no letters. There's no A's or B's or C's to do them to. And there's really no point in doing universal out to a letter if we don't have any letters to do them to. Well, what are we going to do in this problem? We're basically stuck until we can use line 1. And we don't have what we need to use line 1. The main operator of line 1 is the or. If we're going to use it, we need negation of one of the two sides. So I need to write in a show line. This is desperate measures. If there's an or an arrow statement you want to use, you don't have what you need to use it. So I'm going to show it's not true that there is an x fx, right? If I can show that, and I'll show it by indirect derivation, then I can use it. I should be able to show it's not true there is an x fx. I have for all x, not fx up at line 3. So if I do this by indirect derivation, I'll assume that there is an x fx. New show line to show splat. All right, so now I have an existential out to do in line 9. So I get FA. But I can also get not FA from line 3, right? Nothing is F. Then I have a contradiction. Splat, 11, 12, splat in. So I've shown splat. I've shown that nothing is F. Now I haven't shown the splat for line 6. I can't use the splats that are inside a box at 10 and 13. Those are inside a box. I'm not allowed to use them. But now that I've crossed off the show line at line 8, I can use line 8. Line 8 is one of the negation, one of the two sides of 1. So I gotta get the other side. There is an x, rxx. So that's 1 and 8, wedge out. Give that a name. So existential out on 14, I have to use a new name. So I'll use B. Now I have a letter that makes sense to do universal out on 7. So I get not for all y, RBY, right? So that's 7 universal out. Push that negation through again. Sorry, this is supposed to be a backward Z. If you look at line 7, it's the Y quantifier is a backward Z. So I get for all Y, not RBY, 16 not existential out. And then I can change that to a B again. Then I have a contradiction between 15 and 18. Now I can cross off that show splat. Therefore, I've shown this by indirect derivation and this by conditional derivation. Great. Let's do one more desperate measures problem. I'm not going to do both of these because I want to leave one for you to do as practice. But let's do this second one here. So this one's an arrow statement that we're going to need to do desperate measures with. You're not going to know going into the problem it's a desperate measures problem. You just started doing the normal way. So we'll start this by indirect derivation since it's an OR statement. Assume the negation of the whole OR statement. New show line to show splat. Okay, so we can do not wedge out on line 3. Get that. Sorry, not wedge out. Get that. Those will turn into existential statements. Give those names. So do existential out on 7. Get that. New name into existential out. So into existential out on 8, I get it with a new name. So I'll use B. But that still doesn't give me what I need to do line 1, right? So to do line 1, I need the negation. I either need the if part to do most ponens, or I need the negation of the then part to do most tolens. I don't have either of those. There's no obvious way of getting one of those. So what I'm going to do is I'm going to show one of them. So if I show the if part for all x, fx, so that's the if part of 1. I'm writing in a show line to show that because that'll unstick myself from the problem. If there's an arrow statement or statement you want to use and you don't have the other thing you need to use it, write in a show line to get the other thing you need to show it. This is a negation. I'll show it by indirect derivation. Assume for all x, fx, and hx. Show a contradiction. Well, that says everything is both f and h. But I know that a isn't, so if I get that a is both f and h, 12 universal out, I get that a is f. I break that up. That gives me a contradiction between 9 and 15. Right, so now that I've done that by indirect derivation, I can use line 11. It'll give me the other side of 1. One and 11, arrow out. That'll give me the GB and not HB. From that I get GB. That'll give me a contradiction between 19 and 10. So now I've shown this splat, therefore shown that. So the key to this problem was I wanted to be able to use line 1, but I didn't have what I needed. So I put in a show line at line 11 to show what I needed to use line 1. Once I got that, then I can continue the problem. What did I do? This is supposed to be 4. Sorry, not 4. Not universal out on 5. Sorry, 5. Say it's early today. Very good. So that's it for today's lecture. I'll see you in the next one where we're basically just doing review from this point on.